An independent parcel of air, when forced to rise for some reason, naturally cools with height. A discussion of stability involves comparing that standard parcel of air to what's happening in the adjacent atmosphere, specifically the lapse rate, which describes how rapidly the atmosphere cools with altitude. If the ambient air outside the parcel is cooling relatively slowly with altitude, the parcel will quickly find itself cooler than the adjacent air. Cooler air is more dense and tends to sink, arresting the vertical movement of the parcel. This is a stable atmosphere. If the ambient air outside the parcel is cooling rapidly with altitude, the parcel will continuously find itself warmer than the adjacent air. Warmer air is less dense and tends to rise, so the parcel will continue its upward path. This is an unstable atmosphere. This question asks what happens to stability if a change occurs to the ambient air. Let's dismiss choice A first. Without getting into too much detail, a change in water vapor doesn't change the lapse rate meaningfully. It can affect the behavior of a parcel, though. Decreasing the water vapor in the parcel makes it cool more quickly and would increase stability. When warmth is added to the bottom of this standard atmosphere, the lapse rate increases. This often happens when the ground warms the air above it in the afternoon, or when a cold Arctic air mass moves over the warm Great Lakes. This sets up a situation exactly like the unstable illustration earlier, where the parcel will be constantly warmer than the air around it and will accelerate upwards. The answer is B. If the atmosphere is cooled from below, the lapse rate is flattened or even inverted. This can happen when the ground cools at night, chilling the air just above it. The flatter lapse rate will restrain vertical air movement, and if an inversion occurs, this is the ultimate stable atmosphere.